This video is a focused explainer about context windows in coding agents. But the real topic is selection. Engineers often picture a strong agent as one that can swallow an entire repository in a single prompt. That is not how the good systems actually work. They keep building a smaller working set. Instructions narrow the search space. File discovery creates a repo map. Retrieval finds candidate snippets. Compaction keeps the session alive. Subagents partition work into separate loops. I'm grounding this in current official docs for Codex, Claude Code, Gemini CLI, Cursor, and the OpenAI platform as of March 14th, 2026. The core claim is an engineering synthesis. The winning pattern is not bigger prompts, it is better working set assembly. The first correction is conceptual. A context window is working memory, not a source control mirror. OpenAI's current Codex model docs show very large windows, and Anthropic documents 200K windows with an optional 1M token beta for some Claude use cases. That is a lot of room. But it is not free space dedicated only to code. The budget also holds system behavior, repo instructions, conversation history, tool definitions, and the model's own output. As soon as the task becomes multi-step, the transcript itself starts competing with code for space. So the engineering job is not only model selection. The engineering job is deciding which evidence deserves to be in working memory right now. Selection starts before the model reads a single implementation file. OpenAI documents, AGENTS.md, loading from the repo root down to the current working directory. Gemini CLI documents, hierarchical GEMINI.md files, plus just-in-time context files discovered when tools access a directory. Cursor's rules system lets teams define always applied rules, glob-based auto-attached rules, and agent-requested rules, and it can also exclude files through ignore controls. Claude Code's memory system and CLAUDE.md files play a similar role. The shared lesson is that instructions prune the search tree. If the repo already says generated code lives here, tests are run this way, and migrations need approval, the model has fewer branches to explore and fewer files to waste time on. This is the part many people miss when they imagine whole repo prompting. The agent usually starts with maps, lists the files, search for a symbol, check the diff, inspect a directory. Cursor makes this very explicit with @sign references, like at files, at folders, at code, at Git, and at past chats. Gemini CLI documents a file discovery service that powers file-oriented context lookup. In practice, shell tools like grep are perfect for this. They produce small, structured clues. The model does not need every line of every file, just to learn that authentication logic lives under one service directory, and the tests live somewhere else. It needs a high-quality candidate set first. When the repo is too large for direct search alone, retrieval enters the loop. OpenAI's file search and retrieval docs describe vector stores, semantic plus keyword search, metadata filters, and max result controls. Cursor's code-based indexing docs say it computes embeddings for files and indexes new files incrementally. So agent features can recall relevant code later. That architecture is useful, but it is easy to overclaim. Retrieval does not mean the agent now understands the code base. It means the runtime can pull a smaller set of candidate snippets that are probably relevant. The model still has to verify that the retrieved code actually matches the current task, version, and boundary. OpenAI's tool search docs are useful here. They show the same pattern on the capability side. If you have large numbers of tools, the runtime can defer loading detailed schemas until the model has narrowed the candidate set. Claude Code documents tool search for large MCP surfaces for the same reason. This matters because code selection is not the only context problem. Tool descriptions, MCP servers, and auxiliary procedures also consume tokens. So the general rule is broader than code. Large capability surfaces need lazy discovery, just like large code surfaces need lazy reading. Even if the repo slice is perfect, long sessions still break without state management. OpenAI documents compaction as a way to replace an old prompt and response history with compressed history that uses fewer tokens. Anthropic's Claude code memory docs show how project memory and imported files carry forward durable context, while Cursor exposes past chats as summarized context. Gemini CLI documents checkpointing that saves project state, conversation history, and the pending tool call before edits. The shared design point is simple. You cannot keep every prior token forever. The system has to carry forward conclusions, not the whole raw conversation. That makes context cheaper, but it also means stale summaries can become a real failure mode. Subagents are one of the cleanest answers to context pressure. Anthropic documents subagents with their own context windows, keeps specialized work from inflating the main conversation. Gemini CLI says the same thing directly. Subagent interactions happen in a separate context loop, saving tokens in the main history. Once you think in working sets, the value is obvious. Let one worker map dependencies, let another edit, let another run tests. Each one sees a smaller and cleaner slice of the task. The main agent receives findings and artifacts instead of every exploratory step. That is usually better than asking one model loop to carry the entire problem all at once. This is the mental model that replaces the myth of one giant prompt. The agent loads rules, maps the repo, reads targeted evidence, acts, then compresses what it learned. So the next step starts from a smaller state. Good tools make that loop visible. You see commands, file reads, tool calls, and sometimes plan state or task state. That visibility matters because the model quality is only part of the result. The orchestration loop determines whether the next turn has the right evidence. In other words, context assembly is not a setup step. It is the core loop. Once you look at the system this way, the failure modes become more predictable. The agent misses the right file. The repo rules were vague, or generated code polluted search results, or because the retrieval layer ranked stale or irrelevant snippets too highly, or because the summary carried forward a wrong assumption, or because the runtime shoved too many tools into the turn. None of those failures are fixed by simply buying a larger model. They are working set quality problems. That is actually good news for engineers. Repo structure and runtime design are things you can improve directly. The practical takeaway is straightforward. If you want better agent behavior, improve the context pipeline. Keep repo instructions short and operational. Exclude noise from search and indexing. Give the agent concrete starting evidence, such as a failing test, a stack trace, or an exact path. Use retrieval and skills to load heavy detail only when it matters. And if you're building your own runtime, designed for working set assembly from day one, the useful mental model is not that an agent knows the whole repo. The useful mental model is that it keeps earning a better small slice of the repo one step at a time.